What holds our universe together? When we look at galaxies, the stars at their edges are spinning so fast they should fly off into space. Yet they don't. It's as if some invisible mass is providing extra gravitational pull. We call this mysterious substance dark matter. So what is it? Well, we know what it's not. It's not the dust and gas clouds we see, nor is it black holes or dim stars. Dark matter doesn't emit, reflect, or absorb any light, making it completely invisible to all our telescopes. We only know it exists because of its gravitational effects on the things we can see. Think of it like this. Imagine a trampoline representing space-time. A heavy bowling ball, like a star or a galaxy, creates a deep dip. Now imagine an invisible, even heavier ball placed nearby. It creates its own massive dip in the fabric of space-time, affecting how everything else moves. That's what dark matter does. It bends space-time, altering the paths of light and holding galaxies together. Scientists have observed this bending of light, a phenomenon called gravitational lensing. Light from distant galaxies gets distorted as it passes by massive clusters, and the amount of distortion reveals a much greater mass than what we can visibly account for. This discrepancy points directly to the presence of dark matter. According to our current models, the universe is made of about 5% ordinary matter, the stuff that makes up stars, planets, and us. About 27% is dark matter, and the remaining 68% is dark energy, another cosmic mystery. The leading theory is that dark matter is composed of undiscovered subatomic particles, often called WIMPs, or weakly interacting massive particles. These particles would interact with normal matter only through gravity and the weak nuclear force, which is why they are so incredibly difficult to detect. Huge experiments are running deep underground, shielded from cosmic rays, trying to catch a fleeting glimpse of a dark matter particle bumping into an atom. So far, the search has come up empty, but the quest continues. Did you know that everything we see, from the smallest pebble to the largest star, only makes up about 5% of the entire universe? So what's the other 95%? Let's travel back in time to find out how this cosmic mystery was first uncovered. Our story begins in the 1930s. Astronomy was a different world back then, with scientists using massive brass and steel telescopes to gaze at the heavens. One of these brilliant minds was an astronomer named Fritz Zwicky. While studying the Coma Cluster, a massive group of galaxies hundreds of millions of light years away, he noticed something strange. Zwicky carefully calculated the mass of the galaxies in the cluster based on the light they emitted. But when he observed how fast these galaxies were moving, his calculations didn't add up. They were zipping around so quickly that the visible matter, the stars and gas he could see, shouldn't have been enough to hold the cluster together. The gravitational pull was far too weak. By all accounts, the galaxies should have flown apart into deep space. To explain this, Zwicky proposed a revolutionary idea. He suggested there must be some kind of invisible matter, something we can't see, providing the extra gravitational glue. He called it dunkel materie, or dark matter. At the time, his idea was largely dismissed. It was just too radical for many of his peers. Fast forward a few decades to the 1970s. An astronomer named Vera Rubin was studying the rotation of individual galaxies. Using more advanced technology, she observed stars on the outer edges of galaxies. According to the laws of physics, these stars should have been moving much slower than the stars near the center. Just like the outer planets in our solar system orbit the sun more slowly than the inner ones. But that's not what she found. Instead, the outer stars were moving just as fast as the inner ones. It was as if a giant invisible halo of mass surrounded the entire galaxy, giving everything a uniform speed. Her meticulous work provided powerful, independent evidence for Zwicky's unseen matter. Today, with our most powerful telescopes, we've mapped these invisible halos. While we still don't know exactly what dark matter is, we know it's there. It's a fundamental part of our cosmic puzzle, a reminder that the universe is far more mysterious and magnificent than what meets the eye. We know dark matter exists because we can see its gravitational effects on galaxies and stars, but what exactly is it? And more importantly, how do we even begin to look for something that's invisible? Today, we're diving into the ingenious methods scientists are using to hunt for this elusive substance. One of the most powerful techniques is called gravitational lensing. Imagine a massive galaxy cluster sitting between us and a distant galaxy. According to Einstein's theory of general relativity, the immense gravity of the cluster, including its dark matter, actually bends space-time. As light from the distant galaxy travels past, it follows this curved path, creating distorted, magnified, or even multiple images of the background galaxy. By measuring this distortion, astronomers can map the distribution of all matter, including the invisible dark matter that's causing most of the bending. It's like using the universe as a giant magnifying glass. But what if we want to catch a dark matter particle right here on Earth? For that, we have to go deep underground. Scientists build highly sensitive detectors in mines or tunnels, shielded by kilometers of rock from cosmic rays and other radiation that could create false signals. These experiments are designed to spot the incredibly rare and faint interaction of a dark matter particle colliding with the nucleus of an atom, like xenon or germanium. If a WIMP, or a weakly interacting massive particle, which is a leading dark matter candidate, bumps into one of these nuclei, it should produce a tiny flash of light or a subtle vibration that our detectors can pick up. It's a search for a cosmic needle in a planetary haystack. Finally, if we can't find dark matter in space or underground, maybe we can create it. At particle accelerators like the Large Hadron Collider, physicists smash protons together at nearly the speed of light. The immense energy from these collisions can create new, exotic particles. According to theories, if dark matter particles are produced, they would be stable and neutral, meaning they'd fly out of the detector without leaving a trace. Scientists look for events with missing energy and momentum energy that was there before the collision, but seems to have vanished. This imbalance could be the signature of dark matter being created and escaping unseen. From cosmic lensing to underground labs and colossal colliders, the search for dark matter is pushing the boundaries of science. Each method gives us a different piece of the puzzle. While we haven't found it yet, every null result helps us narrow down the possibilities, bringing us one step closer to understanding this fundamental mystery of our universe. Now, let's zoom out. The universe isn't just a random scattering of galaxies. It has a structure, a breathtakingly vast and intricate network known as the cosmic web. On the largest scales, galaxies are arranged in massive clusters, which are themselves connected by long, thin filaments of matter, stretching across hundreds of millions of light years. And what forms this cosmic web? You guessed it, dark matter. These filaments are like superhighways of dark matter, funneling gas and galaxies towards the dense intersections where galaxy clusters form. The visible matter, the stuff that makes up stars and planets, is like cosmic dust caught in this immense gravitational web. It pools and collects in the densest regions, lighting up the underlying dark structure. So, when you see an image of a galaxy cluster, you're only seeing the tip of the iceberg. The real heavyweight, the true architect of this grand design, remains unseen. The search for the dark matter particle is one of the most exciting frontiers in modern physics. Scientists are using giant underground detectors and powerful telescopes to try and catch a glimpse of this elusive substance. Uncovering its identity will not only solve one of the biggest mysteries in astronomy, but will fundamentally change our understanding of the cosmos. The universe is far grander and more mysterious than it appears, held together by a force we are only just beginning to comprehend. What if we're on the verge of a breakthrough? Imagine a new generation of space telescopes far more powerful than anything we have today. These aren't just bigger lenses. They're advanced observatories designed to hunt for the faintest gravitational whispers of dark matter. Orbiting far from Earth, they'll map the universe with unprecedented precision, looking for subtle distortions in starlight caused by massive, invisible structures. These telescopes will essentially give us a new pair of eyes to see the unseen, peeling back a layer of the cosmos that has been hidden from us since the beginning of time. Back on Earth, the hunt continues deep underground in futuristic laboratories. We're building detectors so sensitive they can spot the ghost-like passage of a single dark matter particle. Think of vast, pristine chambers shielded from all cosmic noise, waiting for that one tiny, almost impossible interaction. These experiments are pushing the limits of technology, using exotic materials and extreme cold to create the quietest places in the universe, all in the hope of finally catching a glimpse of this elusive particle. But how do we make sense of all this new data? That's where artificial intelligence comes in. Supercomputers running advanced AI algorithms will sift through petabytes of information from telescopes and detectors. They'll run countless simulations of the universe, creating digital cosmoses from the Big Bang to the present day. By comparing these simulations with our real-world observations, AI will help us test theories and zero in on the properties of dark matter. It is like having a brilliant partner that can see patterns we could never spot on our own. Solving the dark matter mystery won't just fill in a blank in our cosmic textbook. It could revolutionize physics, revealing new particles, new forces, and maybe even new dimensions. It's a journey into the unknown, a quest that combines human curiosity with groundbreaking technology. The future of astronomy is bright, and the secrets of the dark universe are waiting to be revealed. Our journey through the cosmos brings us to one of its greatest lingering mysteries. We've mapped the stars, charted the galaxies, and measured the echoes of the Big Bang itself. Yet, for all we can see, we're faced with an incredible truth. Most of the universe is missing. This isn't science fiction. It's the frontier of modern cosmology. Each null result, each failed detection isn't a defeat. It's a vital clue, narrowing the search and pushing our creativity and technology to new limits. This quest is more than just a search for a particle. It's a reflection of our own innate curiosity, the same drive that led our ancestors to look up at the night sky and wonder. We are a species defined by our desire to understand the unknown, to pull back the veil and see what lies beyond. The search for dark matter is a testament to human ingenuity and our relentless pursuit of knowledge. It reminds us that for all our discoveries, the universe still holds profound secrets. The next discovery could come tomorrow or in 100 years, but one thing is certain: we will never stop looking. The darkness holds the key, and our journey into it has only just begun. Thanks for watching, and don't forget to subscribe for more journeys into the unknown.